Hello dear students, so again I'm back with the chapter wise solution series. Sorry for the delay in this one. So today I'm taking this kinetic theory of gases given in that NTA Abhyas JEE chapter wise test. So on the paper 9th and 15th are the same question. Question number 14 answer is not rightly given. Otherwise all in all the paper is a really good one to practice for the kinetic theory of gases. I have marked what are easy, what are medium and what are tough. So based on this analysis, what I feel, good enough student who is just preparing 80 plus must be a score you should get, and for the students who are doing very good, 100 plus must be the aim for this particular chapter. But I think it's a nice way of practicing like the other test. So just enjoy the solutions and do give us your feedback, how you like them or not. So let's begin. Question number 1. Of the following graphs, the one that correctly represents the variation of a quantity beta defined as minus dV by dP by V with P for ideal gas at constant temperature. So these are very standard profiles. Ideal gas at constant temperature simply means T is constant, or you say PV is constant, and you know for an isotherm dP by dV is minus P by V. So here it is dV by dP. So dV by dP you can write as minus V by P. So therefore this quantity beta, negative of dV by dP divided by V, that basically reduces to that minus become plus V by P by V, that is 1 over P. So the variation with pressure would be 1 by P, that is it is going to be an inverse curve. So looking at the four options, only first one satisfies. This is the inverse relationship, so you can do it like that. Now next one. Two containers of equal volume contain the same gas at pressure P1, P2, absolute temperature T1, T2 respectively. On joining the vessels, the gas reaches a common pressure, that you know whenever you connect two vessels the pressure will become same, and if there is no alternating heating cooling arrangement, the temperature also becomes same like that. So the ratio P by T is, so this is a very you can say a standard profile asked many times. Let's say this is the first chamber, this is the second chamber. Initially let's say they were not connected, this was P1 and it was T1, and volume let's say equal volume, so let's call it V, you can say it V0 or V only, write it like this. This is P2, T2 and V. Now when you connect them, let's say like that, let me draw it more properly. So when you connect it, let's say like this, the valve is open. So finally what you will have, both will have the same pressure and temperature, volume of the both part will remain same. So what happens during this? So you know, first of all the moles are going to remain constant. Some gas might go from 1 to 2 or from 2 to 1, but the total moles must remain same. So N1 initial plus N2 initial would be N1 final plus N2 final. And you know N is PV by RT, so I can write it as PV 1V upon RT1 plus P2V upon RT2. And finally I can treat both as the same chamber, the pressure is common, the final volume becomes 2V and temperature becomes T. So what I can do, this V R I can take it out. So P1 by T1 plus P2 by T2 is equal to 2P by T. So the ratio what you need, P by T. So therefore P by T is now very easily you can write it as P1 by 2T1 plus P2 by 2T2. So look at the options, which option is satisfying. I think the D1 is the appropriate or the right one. Next one. An ideal gas is found to obey an additional law of V into P square equal to constant. You know ideal gas is there, so PV equal to nRT has to be followed for sure. The gas is initially at temperature T and volume V. When it expands to volume 2V, the temperature will become. So here we have to take a relation between V and T. So what we are given, P square V is equal to constant. So what we can write, P square V is equal to constant, you can write it as we need a relation between V and T, so better write P as nRT by V. So nRT by V square into V is equal to constant, N and R will be constant. So you can directly do it like this. This will become T square by V equal to constant, rest all are constant. So T square is proportional to V, or T square by V is constant, you can write like this. So if the volume is doubled, square of the temperature will be doubled. So T square becomes double, that means temperature would be root 2 times. You can directly make it out. So you can say T is proportional to root V. So volume is doubled, temperature will become root 2 times. Directly you can do this. Next one, always do such question like that. Similarly, you see this next one. A gas expands adiabatically, written at constant pressure. Okay, it expands adiabatically at constant pressure also, such that its temperature T is proportional to 1 by root V. Now this is something which is very typical. It's tough to say it is isobaric as well as adiabatic, but I'll go with adiabatic word only. So T is proportional to 1 by root V, where V is the volume, the ratio of the Cp by Cv would be. So I know it, I can write it as Tv to the power half is constant, you can write this. And we know for an adiabatic process Tv to the power gamma minus 1 is constant, that's a standard one, or you write as PV to the power gamma is constant, it's one and the same thing. You just use PV equal to nRT and you get this. So comparing it, you can directly say gamma minus 1 is 1 by 2, so gamma is 3 by 2. I don't know what they want to say by constant pressure, but you going by the adiabatic, I can go with 1.5. Next one. Two soap bubbles of the radiuses x and y coalesce to constitute a bubble of radii z, that z is. Now for the soap bubble, you know soap bubble has a thin soap film and you have that air inside. So what we had first two bubbles, one of radius x and one of radius y, and finally they joined to form a bigger bubble. So what we understand, you know, using the concept of the surface tension, you will say the pressure inside it would be this P1 was P0 plus 4s by r, you know, because 4s, because there are two layers, basically what we make it, because there's a thin film here, and similarly here the pressure would be P0 plus 4s by y, and similarly you can write this pressure P3 would be P0 plus 4s by z. And just when they coalesce, we always take this to be an isothermal process, and we will say the PV product or the moles constant, whatever you can say, the PV thing also remains constant. So what you can directly write, you can say the final pressure, or I write it as P only. So PV would be equal to P1 V1 plus P2 V2. The amount of the gas will remain the same. So just a moles constant and temperature constant, this is the standard thing you write. So what you have, P0 plus 4s by z into Vv, you can write it as 4 by 3 pi r cube, so it would be 4 by 3 pi z cube. And this P1 you write as P0 plus 4s by x, and here what you will have, 4 by 3 pi x cube. Here what you will have, P0 plus 4s by y, 4 by 3 pi y cube. So 4 by 3 pi, I can take it out, it will look better. And now, so what you have P0 z square plus 4s by, what you can say, it was z cube, sorry, plus 4s by 4s into z square would be equal to, what you can write it as, you can write now this as what we can say, P0 x cube plus 4x x square plus P0 y cube plus 4s y square. Now there is nothing written like P0, so it would be a tougher thing. So let's assume it is in vacuum, because we don't have any other thing, otherwise we cannot get a direct result. The P0 won't be cancelled. So taking that P0 to be vacuum thing and taking it to be 0, these terms get cancelled, and now the 4s factor gets cancelled, and you will write z square equal to x square plus y square. But here you will have to take an assumption, otherwise you won't be able to solve the question. So using it, you can write it like this. So the answer becomes option A in that particular case. So you have to assume that they are coalescing inside a vacuum, not in the normal atmosphere that we usually have. Next one, vessel contains a gram of oxygen at this pressure and temperature. Found that because of the leak, the pressure becomes 5/8 of the original value and temperature falls. Find the mass of oxygen that is leaked out. So here important thing, there is a vessel. So what we will have volume is going to remain constant. So volume is going to remain a constant, and now if the volume is constant, you can say find the mass of the oxygen that is leaked out. You need to find it out. So what we will have, because volume is constant, what I can say, you know, number of moles you write as PV by RT. So volume is same, so volume I can write it as let's say N initial RT initial upon P initial, that should be equal to N final RT final upon P final. So what would be the final moles remaining? I can write it as initial moles into R, and R I can cancel up, and what I will get, this is P final over P initial, and this is T initial over T final. So put it initial moles, whatever they will be, I'll check it out. P final upon P initial, it is given at pressure drops to 5/8, so it will become 5 by 8. Ti by T final, always remember capital T means it is in Kelvin. 47 will means 320, and this becomes 300. So this 0 and 0 get cancelled, this becomes 4, this 5 things will get 6, this will become 2 by 3. So that means 1/3 moles has leaked. That is the amount of moles that has leaked. 1/3 of the initial mole, or you can say the 1/3 of the initial amount, you can directly say. So because moles is 1/3 leaked, so mass also 1/3 would be leaked. So 1/3 of 1 gram. So 1 by 3 gram will leak and 2 by 3 gram will remain. So you can do it like that. Next, For a gas, the ratio of specific heat at constant pressure and constant volume is gamma, then the value of degree of freedom is, gamma is equal to 1 plus 2 by F. So what you can write, F, you can write it what you can say, it would be better write it like this, gamma minus 1. So F would be, what you will have, it would be the value of degree of freedom, yes, you have gamma is equal to 1 plus 2 by F. So F would be equals to 2 upon gamma minus 1. Yes, this option was there, I was searching, the option was not visible, so it should be D. Yes, so that's an easy one, not a tough one. Now a mole of diatomic gas undergoes a process like this, where P naught and V naught are constant. The translational kinetic energy of the gas when V is equal to V naught. So when V is equal to V naught, what would be the pressure? It would be P naught. Just check it out. This is the mistake in this question the people do. I have seen this question multiple times. I usually give it in my exercise sheets to my student. So the pressure at V equal to V naught would be P naught upon 1 plus V equal to V naught. So it is 1 plus 1 ka whole cube. So that would be equal to P naught by 2. So now this is the pressure at this thing because it is a diatomic gas, and what we will have, we have this PV equal to nRT because it is an ideal gas, we assume. So what we have, PV equal to nRT. So what would be the temperature, or what would be the value of nRT? You can directly say the value of nRT is going to be PV, P is P naught by 2 into V naught. And for a translational kinetic energy, translational kinetic energy for mono, dia, tria, for everyone it is 3 by 2 nRT, that everyone knows. So it would be 3 by 2 into P naught by 2 into V naught. So it would be, sorry, it cannot be cancelled like this. Let me undo this. So it becomes 3 by 4, it won't be cancelled. 3 by 4 P naught, V naught. So option B is the most appropriate one for this. Next one. The average translational energy and the RMS speed of molecule in sample of oxygen at 300 Kelvin are given this and this respectively. The corresponding values at 600 Kelvin will be. So temperature is doubled, so Vrms is proportional to root T. So if temperature is doubled, it will become root 2 times, so it will become 484 into root 2, let's say that is 1.4 roughly. So if I do 14 4s are 56, 14 8s are what we have, 140, 28, I can 112 and 517 and 11 goes there, and it would be 14 4s are what we have, again 56 and 11, that is 67, so 677.6. so most appropriate is 684. I think that would be the closest one. Now what would be the translational kinetic energy? Kinetic energy is proportional to T, so that will become definitely double. So it would be double, so 6.21 is doubled, so 12.42. so go for option D. That's an easy one if you remember these things very well. In the absence of intermolecular forces of attraction, the observed pressure P is going to be. So in the absence of intermolecular forces of attraction, just remember, it is not saying absence of intermolecular forces, it is saying forces of attraction. That means only repulsive thing is going to be dominating. So there will be no stickiness. So definitely what will be happening, the observed pressure P, what happens to it? So for this question, I'll advise you just read the page number 151 of your NCERT states of matter from the chemistry one, where they explains that at high pressure what happens, because of the attractive forces, the molecules don't hit the wall with the force they actually should have been hitting. So if those forces of attraction would be absent, they would be hitting it more hard, and you will see the observed pressure definitely would be going to be greater than P. So that is the most appropriate solution you can go for this. So just read that paragraph there on page 151 on states of matter chapter. So that would be more helpful for you. Next. Vessel contains a mixture of a mole of oxygen and 2 moles of nitrogen at 300 Kelvin. Ratio of the average rotational kinetic energy per O2 molecule to per N2 molecule. So ratio of the average kinetic energy depends only on the temperature, and both are of the same type of gas. So it is going to be 1:1. It is independent of the amount. So you can directly go for option A. Both have 2 degrees of freedom because of rotation, and temperature is same, so the average value will be same. Gas mixture contains 2 mole oxygen, 4 mole argon, neglecting all vibrational modes, the total internal energy. So vibration you have to neglect first. 2 moles of oxygen. Oxygen is diatomic, so what we will have 2 into 5 by 2 RT. Argon is the mono, that is 4 into 3 by 2 RT, that you can directly say. So it becomes 5 RT, it becomes 6 RT, so it becomes 11 RT. So that's an easy one for you. Go for option D like that. Next one. An ideal gas is taken along the cycle ABC as shown in the PV diagram. The total work done by the gas during the cycle is, that is equal to the area under the curve. So the area under the curve is half, this gap is 2V and that gap is 3P. So what you will have it is equal to 3PV. That's an easy one for you. Directly the area of the triangle. Next one. a liter of oxygen at a pressure of atm and 2 liters of nitrogen at a pressure of 0.5 atm are introduced in a vessel of volume 1 liter. If there is no change in temperature, the final pressure of the mixture of the gases is going to be. Okay, so first of all, what we have, a liter of oxygen at a pressure of 1 atm, and you are given the temperature is still the same, so just applying PV equal to nRT here. So the pressure is 1 atm and the volume is 1 liter. That would be equal to moles of O2, whatever we can say, into R into T. Similarly, for nitrogen, what you have, 0.5 atm and 2 liters, that would be equal to N of N2 into RT, and temperature is still the same, so you can say the value is same. That means NO2 is equal to NN2. That is the first thing that you can say. Into a volume, into a vessel of volume a liter, if there is no change in temperature, the final pressure of the mixture of the gases is going to be. So first of all, what you have the first thing that the moles of both are same. So you have the both are having the same moles. Now what we will have, finally also we can write PV equal to nRT for the complete system. So final pressure, final volume is 1 liter, final moles would be double, and I can write them as 1 plus 1 RT, 1 by RT plus 1 by RT. I can have a 2 by RT in those units multiplied by RT, and the temperature is still the same. So the pressure, I can write it as atm liter. That would be a better thing. So pressure is directly 2 atm, that we can directly make it out in this particular case. So volume was 1 liter, there is no change in temperature, the final pressure of the mixture of the gases now would be, so no other option. I think this must be some mistake, it should be 2 atm. So none of the option is right now. Now move forward, can't help. Next one, the average translational kinetic energy and speed. I think this is a repeated one. We did it or it was some mistake on my end. I think we did this question. Okay, this was question number 9. I think this is the same one. So no point we remember the result, it would be option D. So repeated question. Next one, the RMS velocity of hydrogen at 300 Kelvin is given, and the RMS of oxygen at 1200 Kelvin is. So you know VRMS, the formula everyone knows, is root 3 RT by M. So what we require for oxygen at 1200 to the ratio of the hydrogen at 300, if we do this R and this thing will be same. Now the temperature of O2 is 1200, temperature of that was 300, and mass inverse H2 is 2 and O2 is 32. So this is 4, this is 8, this is 1 by 4, so this is 1 by 2. So VO2 at 1200 and VH2 at 300, ratio is 1 by 2. So the oxygen speed would be half of this, so 1930 divided by 2. So I think this is 965 meter per second. Go for it, meter per second, not second square. So again a mistake. Gas is present in a cylinder fitted with movable piston. Above and below the piston there is an equal number of moles of gas. The volume above is 2 times the volume below at a temperature of 300 Kelvin. Temperature at which the volume above be 4 times the volume temperature at which the volume above be 4 times the volume below. I don't think what it wants to say. There is some sort of a typo error. I feel it must be there. Let me try one thing. Okay, a gas is present in a cylinder fitted with a movable piston like this. So I have a thing, there are both chambers, there is one chamber upwards, one is downwards. There is an equal number of moles of gas. Moles are equal, volume above is 2 times the volume below. Okay, so it is V, so it would be 2V, I can say, at a temperature of 300 Kelvin. Okay, temperature at which the volume above be 4 times. Okay, I think the temperature of the both part must be the same. So what we are given there's a piston also, and below and above, so there must be, what we can say is the balancing thing must be there. What we need to have, what we can directly say, the P bottom into area minus P top into area must be equal to mg in any condition. So initially what we have, P bottom minus P top, what we have, both temperature is given. So the pressure we say is nRT by V. Typically what we write it as nRT by V, or you can say nRT, your pressure is nR, so n is n, r is, this is 300 over V. I can write it as V, and this is A, or we can write this V as A into, let's call it this thing as L by 3, and this would be 2L by 3. That would be a better thing. I think that would be a better way to write it. So A into L by 3, and this is A minus what we have NR into 300, and this would be what we have at the top is 2A L by 3 into A equals to mg. So that is the first equation. Now what you need, temperature at which the volume above be 4 times the volume below. So in that particular case, what we can make it out, what we can directly say, in that particular case, again this thing which should be remaining the same. There it would be, the moles would be same, NR into T upon A into what I can say, the volume above is 4 times, so it is A into L by 5 into A minus what we can say nRT upon 4A L by 5 into A, that would be equal to mg. That is what we can say. So using the data above, or better what we can do, it's better we can divide both the things. So if we can divide or we can equate the both the side, that would be a better thing. So what we can have, 3 into 300 minus what we will have 300 into 3 by 2, that thing would be equal to 5t minus what we will have 5t by 4. Okay, so that's a good thing that we have got. So this is 900, 450, I can make it out. This would be 5 minus 5 by 4. So what we can do, 5 minus 5 by 4, if I'm not wrong yet, yes, it is the right thing. So it would be 20 minus 15, 15t by 4. So t would be 450 into 4 by 15. So this is 30 into 4, 120 Kelvin. So question was really good. You need to think like that. So I'll let me draw it once more for you. So here I said it would be L by 5 and it would be 4L by 5, and you have to do against this, and in both the cases the mg, you draw the free body diagram. This is P from top into area, this is P from bottom into area, and this is mg. So for equilibrium I have done both the things, both the equations would be like that. 18th one, the ratio of velocity of sound in hydrogen and velocity of sound in hydrogen and oxygen at STPs. So velocity of sound in a gas you know is gamma RT over m. So the ratio at the same temperature would be this VH2 by VO2. So if I do the gamma of H2 and O2 is same, so it would be only the mass thing. So it would be 32 by 2, so 16. So you can say it would be 4:1. That's an easy one, a very general question asked many times. Next, ideal gas expanded adiabatically, how many times its initial volume should be expanded to reduce the RMS by a factor of 2? You know Vrms is proportional to root T. So to become it half, temperature should become 1 by 4. Now you know for the volume you have relation TV to the power gamma minus 1 is constant. So what we can say, volume, you can say volume to the power gamma minus 1, or you can say TV to the power half is constant, or you can say T is proportional to 1 by root V, or V is proportional to 1 by T square, I can say. So temperature becomes 1 by 4, so volume should become 1 by 4 whole square, so that should become 16 times, I can guess. So it would be 16 times, the volume must become 16 times for the required result. Next, temperature at which the kinetic energy is half the value of 327. So 27 means 300 Kelvin. For kinetic energy to half, temperature must be half because it is proportional to T. So it is 150 Kelvin. So if you convert it into Celsius, it would be minus 123. So be careful about the units. That is the only catch here. VT graph at atmospheric pressure for a monoatomic gas. Okay, for a monoatomic gas, what we have, we know PV equals to nRT. So at atmospheric pressure, that means pressure is fixed, moles is fixed, R is fixed. I think that the volume is proportional to temperature, and it is in Celsius. Ideally it should be like this in Kelvin. This should be the V by T in Kelvin, so it should be like that. So volume will become 0 when temperature is 0 Kelvin, or you can say it is minus 273 degrees Celsius. So it would be like this, a straight line like this. So the most appropriate thing that you can say, the Charles law discovery, this is option A is the most appropriate. Very good question asked. Next one, 3 perfect gases, absolute temperature, mixed, masses of molecules M1, M2, M3, and the number of molecules N1, N2, N3. Assuming no loss of energy, the final temperature of the mixture is going to be. So assuming no loss of energy, so energy remains same. So what we have, kinetic energy is 3 by 2 nRT. So what we have, NT product will remain same. So N1 T1 plus N2 T2 plus N2 N3 T3 would be equal to, finally moles would be N1 plus N2 plus N3. R have cancelled already, and that would be T mix. So T would be N1 T1 plus N2 T2 plus N3 T3 over N1 plus N2 plus N3. So that's an easy one for all of you. So go for option A in this case. Now next, the gases carbon monoxide and nitrogen at the same temperature have kinetic energies E1, E2 respectively then. So when is carbon monoxide and when we say is the nitrogen, both we say are diatomic, so both have same degree of freedom and temperature is same, so energy will be same. So that's an easy one for you. Next one, pressure of an ideal gas is increased by keeping temperature constant. Okay, so temperature is constant, pressure is increased by keeping temperature constant. What is the effect of kinetic energy of molecules? So you know, kinetic energy of molecules depend only on temperature, so that is going to remain the same. Again the question on the same concept. Next, monatomic ideal gas at temperature T1 initially enclosed in a cylinder fitted with a frictionless piston allowed to expand adiabatically to temperature T2 by releasing suddenly. Okay, if an envelope or the length of the gas column before and after, then T1 by T2 is, so what we usually write, T1 V1 to the power gamma minus 1 would be T2 V2 to the power gamma minus 1. Gas is mono, so gamma is 5 by 3, 5 by 3 minus 1 is 2 by 3. So T1 you can write volume as A into L1 to the power 2 by 3, T2 A into L2 to the power 2 by 3. So what we have, so T1 by T2 you can directly make it out as L2 by L1 to the power 2 by 3. I think which option is correct? This is option D. That is what we are writing here. Next, which of the following will have maximum kinetic energy at temperature 300 Kelvin? Okay, maximum total, not the translational one. Okay, so what we have, a kg of hydrogen, half kg hydrogen, half kg helium. Helium is monatomic, so energy would be slightly reduced, so it won't have the more energy. Again, it won't have more energy, definitely 1 kg H2 because it is complete diatomic. In rest you have a part of monatomic, so that would be lesser. So the best option is A. That's an easy choice for you. Next, suppose a container is evacuated to leave just one molecule of gas in it. Let V and Vrms represents the average speed and the RMS speed of the gas. Because there is only one molecule, so the everything will be same. You take a single average or the square average, that would be same. That's a very good question asked on what basically is a V and what is RMS. The beautiful question this one. That's an easy one but a very nice question. Next, it's like if you are the you have only one subject mark, so that would be your percentage and that would be your average, everything you can say like that. At room temperature, the RMS speed of the molecules of certain diatomic gases, the gas is hydrogen, that we have done in the one of the question. I just remember, you can also do it like that. What you can say, Vrms you know is what we have, root 3 RT by M. So the molar mass I can find it out by 3 RT by V square. So 3 into R you write as 25 by 3, temperature is room you take as 300 and V square is 1930 into 1930. So what we will be left with, 25 into 3, that is 75, that 2 zeros cancelled, 193 into 193, that is kg per mole. So for grams I can write it like 1000. So 75,000 over 193 into 193, that we are left with. So if you do this approximately comes out as let's say, what we can say, this would be something what we can say closer to a figure of 4. So that would be, if you solve it, comes out as 2 gram approximately if you do. So that would be like that. In one of the question the data was given, so I just intuitively take that, but on solving also it will come like that. 5N and 5N moles of monodiene non-linear polyatomic which do not react chemically with each other respectively are mixed at room temperature. So because it is room temperature, we won't consider the usual vibration, we will only consider the rotational degrees and the translational degrees. The equivalent degrees of freedom of the mixture is going to be. So how you will write the equivalent degrees of freedom? So first of all, what we will say, we will write CV equivalent. CV equivalent you write it as N1 CV1 plus N2 CV2 plus N3 CV3 over N1 plus N2 plus N3. That is the usual way we write. So what we will have, it would be 5N into mono. Mono means 3R by 2 plus N into 5R by 2, and for linear polyatomic and non-linear polyatomic it is 3R, and this would be 5N, sorry. So N1 plus N2, this would be 11N. So this is 15 by 2 plus 5 by 2 plus 15, I can write like this, NR over 11 and get cancelled. So what we are left with, so what we have it as 15 by 2 that is 20 by 2 that is 10, 10 plus 15 that is 25 by 11 r, and you know CV equivalent that would be equal to F by 2r. So F comes out as now 50 by 11, that is the appropriate option. Go with option D in this particular case. Next one, diameter of gas molecule is given. The mean free path of the gas molecule is, you know, the lambda mean free. So you know the formula for the mean free path is 1 upon root 2 pi d square NV. NV is the number of molecules per unit volume, which we typically write it as pi d square, as this is pi, sorry, not small n, and this is NV is what we have, number of moles into Avogadro number divided by volume. And what we can have this n by v, what we can say is volume is nRT by p, so it is 1 upon root 2 pi d square n na, and v I can write it as nRT by p. P I can take as above, so not above, it won't go above, above will be here above, not that above, by p like this. So this nn goes, and what we are left with, it is RT upon root 2 pi d square na into p. But here the value of k is given, and you know r upon na is the Boltzmann constant, so it becomes kt upon root 2 pi d square into p. Now we have to substitute the value. Let me check the value. If you are going to substitute k value written 1.38 into 10 to the power minus 23, and what we have at NTP, the temperature we take as 273, root 2 pi I can write it as 3.14, d square 2.4, that is 5.76 into 10 to the power minus 20, and pressure is at NTP you take as 1.01 into 10 to the power 5. So what we are left with now, this you have to do the calculation. It is not going to be a easy one for sure. Minus 23 minus 20, so I can write minus 3 and minus 5, so I can 10 to the power minus 8 into 273 into 1.38. what we are left with, root 2 is 1.4 into 3.14 into 5.76 into 1.01. so going by all this 1.38 and 1.4 roughly you can cancel up, and 273, 5.676, 4 over 3.14. so if you do all this thing, this basically comes out approximately closer to this 10 to the power minus 7. I have done using a calculator, you should do yourself. So that is the paper. So and this was the all in all the paper, and it was a nice little practice. Usually in JEE there are some very, you can say, the questions which are out of the box. I don't know how to solve them, that the factor is proportional to something or like that, which you don't really recall. There are some very, you can say, very monstrous questions being asked in JEE Main, but none of that was there in this paper. Thanks for watching.